Hi, good evening, everyone. For now, we are waiting for more people to join. As of now, two of you have joined, so let's see if more people are joining. Let's wait for 5 minutes, then we'll start. I hope you can hear me, right? You can drop me a text also if you cannot not be able to speak, please. Okay, so it's already 6:10. I think nobody else is going to join. So I'll maybe start the session for today. Okay, so good evening, those who have joined. I hope you can hear me and see my slide. If there is any problem, please do let me know in between as I present. Okay. So this tutorial class or doubt clearing class is for week 2, which is supposed to be happening on the basic parameter and phase equilibrium. And this course is instructed by Professor T.V. Bharat from IIT Guwahati, and I'm the PMRF teaching assistant, Satyam Tiwari from ITSM Dhanbad. So for this lecture, basically will be just give me a second. Okay, so for this lecture, I'll be presenting. First, we'll start with the assignment which we did in the last class. So there was a question that in Proctor compaction test, the compaction energy depends on what? So there is a correction in that one. That actually the Proctor compaction test in the Proctor compaction, the compaction energy depends on the weight of the hammer and height of the fall. These are the two factors which defines that how much energy is transferred to the sample for the compaction. But the cross section of the compaction mount that decides that how much compaction is happening, but it is not contributing anything to the compaction energy. Okay, so for this one, the right answers will be first and second. Okay, so now coming to the week 2 of the class, week 2 of this course. So there are a few basic terms which we need to understand before we go going further into unsaturated soil mechanics. The first one is the air density. Okay, so as we know that the air density is it basically depends on how much pressure is there in the atmosphere and what is the temperature of the atmosphere, right? Who else is trying to join? Okay, there's no one else. Okay, so it depends on how much pressure is there. So the basic quantity which is depends on the this UA, that is the pore water pressure, pore air pressure, and if we talk about the soil, then pore air pressure or the air pressure and the molar mass of the air. Okay, and apart from that, the R, which is a constant, that is universal gas constant, and it depends on the temperature. This temperature is in Kelvin. So this is the formula from which you can compute the air density, right? So if we quickly do an example on calculating how to calculate a air density. So the example is that if air pressure is 100 kPa and the temperature is given as 24.5 degrees Celsius. Okay, and the given molecular mass of the air is 29 kilogram per kilomole, and the universal gas constant, as we know, 8.314 Newton meter per more Kelvin. Okay, then we need to determine the corresponding air density. Okay. So as the formula states, the air density depends on the this air pressure. Okay, the air pressure is UA, that is given by 100 kPa. So we need to convert it into the Newton meter square, right? So we'll multiply 100 by 10 to the power 3. That will give us 10 to the power 5 Newton per meter square, right? Then the next term will be the molar mass of the air. The molar mass of the air or the molecular mass of the air is given as 29 kilogram per kilomole. So we'll convert the kilomole to mole. So that will be 29 into 10 to the power minus 3 kilogram per mole, right? So we are taking care of the unit so that they will cancel out and we'll finally get the density of the air. Okay. Then the next term is the universal gas constant, that is 8.314 and Newton meter per mole Kelvin. And then the next term is to change the temperature into Kelvin. Okay, so 24 degrees Celsius, that will be converted to Kelvin by adding the number, that is 273.15 or 273.2. So after we add it, then after calculating, we'll see that 10 to the power minus 3, 10 to the power 3 will cancel out. And when we calculate this into calculator, we'll find out the value will come out to be 1.172. The unit will be kilogram per meter cube because mole will cancel. Okay, the Kelvin temperature will cancel out and the meter square here and 1 meter here, Newton is here. So Newton will cancel out and you'll see meter square plus meter cube, and a kilogram will be left there. So the value will be 1.172 kilogram per meter cube. Okay. So in this way we can get the air density, right? But when we move further, that will in the theory class it has been taught that this formula for the air density states good. This formula for the air density states good for conditions when relative humidity is zero or in the dry condition. So this formula can be used to calculate the air density in the dry condition or the RH value is zero. But when there is a relative humidity, okay, in the air, at that time we'll need to, there's a modified formula which we need to use to obtain the moist air density, right? So as we'll see from this example that it is given that at a relative humidity of 50% and an air pressure of 100 kPa, which will need the question asks that which temperature leads to a higher air density, either 0 degrees Celsius or 45 degrees Celsius. So the data given here is the molecular mass Wa is given. Apart from that, the universal gas constant R is given, and we also have molar mass of the vapor, that is Wv. Okay. What we need to calculate? We need to calculate the air density at moist condition, that is basically at 50% RH. Okay. So to calculate that, what we'll do first, we'll need to calculate the air density considering that relative humidity is zero or in the dry condition. Okay. Then the formula for the moist states that dry density of the air minus this term, right? So, okay. So for this, what we'll do that first we'll calculate the density at dry condition. So we'll take rho d is equal to u dry or the pore air pressure at dry condition, that is given as 100 kPa. So multiply 100 into 10 to the power 3, similar to the last problem, and then we'll multiply the molecular mass of the dry air. That is the molecular mass of the dry air is given as WA or a WD, you call it 28.966 into 10 to the power minus 3 to convert kilomole to mole. Okay. Then we'll divide by the universal gas constant R, the value for which is 8.314 again, 8.314, and the temperature which is there is in the first case, the temperature is given as first we are calculating for 45 degrees Celsius. So the temperature is 45 plus 273.15 or 273.2. So that's going to be 318.2. 2 Kelvin. So when we'll calculate this, we'll find out the value for the dry air density comes out to be 1.095, right? And but now we need to calculate the dry density in the moist case when the relative humidity is zero point 0.5. Okay, so the formula for which states that dry density of the density of air as a moist case is equal to the dry density minus 0.611 times WA, that is molecular mass of the dry air, upon molecular mass of the water vapor, okay, or the vapor, minus 1 exponential 17.27 T minus 273 upon temperature minus 36 multiplied by again molecular weight of vapor into relative humidity, what is there, and gas constant and temperature. Fine. So it's a little big formula. We'll one by one put the values in the formula. So the dry density which we obtained is 1.095. So at the place of dry density, we'll put 1.095. Okay. Then we'll write 0.611, and here it will come the molecular weight of air. The molecular weight of air is given as 28.966, and the molecular weight of vapor is given at 18.016. Fine. Then minus 1, bracket closed. Then we have the second term, that is exponential term, exponential or e to the power 17.27, that is constant, multiplied by T, the temperature in this case in Kelvin is 318.2 or 45 degrees Celsius. That is converted to Kelvin here. Okay. Then we'll find that the temperature changes, temperature becomes 318.2 Kelvin minus 273.2 and divided by 318.2 minus 36, T minus 36. The other term that is there is the WV, that is the again molar mass of the vapor, that is going to be 18.016 multiplied by relative humidity 50%, or we can write it zero point 0.5 in fraction. Okay, the R value, the universal gas constant is 8.314. That will be multiplied by the temperature again 318.2 Kelvin. So after solving this, we'll get okay. So after solving this, we'll get the moist. We'll get the air density at the moist condition, that is at a relative humidity of 50%. That will be equal to 1 point. That will be equal to 1.075 kilogram per meter cube. Okay. So in this way, we can calculate the moist density at any relative humidity. Okay. For the second case, let me see, where's the eraser? Okay. So, so here, if we in the B case, that is for the temperature of 0 degrees Celsius, we calculate the temperature becomes 273.2 Kelvin. Okay, and just like the first case, first we'll calculate the dry density, considering the relative humidity is 0. So the formula will be the same, UdWd upon RT. Okay, at the value of the UD, we'll write 100 into 10 to the power minus 3, and at the place of WD, that is the molecular weight of dry air, that is given as 28.966. So that will be 28.966 in 10 to the power minus 3 kilogram per mole. Moving further, we'll write the gas constant here, and the temperature is going to be 0 degree or 273.2 Kelvin. Okay, so it will be 273.2 Kelvin. And after solving this, we'll get a dry density of the air, considering zero humidity, is 1.257 kilogram per meter cube. Now the same exercise as we did in the last case, this one we need to repeat for this case also. So here for rho A moist, we'll have rho D minus 0.611 and multiplied by 28.966 upon 18.016 minus 1. Right? The exponential term 17.27, the temperature here T minus 273.2, T minus 36, and here the WV term, uh, the molecular weight of vapor 18.016, and multiplied by relative humidity upon R, the gas constant, and the temperature. So after solving this, this will become 0. So this term will vanish. So it will basically again come as the same, right? 1.25275. Okay. So we'll see when the temperature is 0 degree Celsius, the moist humidity of the air is 1.274. Okay, 0 degree Celsius, moist density of the air is 1.274. When the temperature is 45 degrees Celsius at the same humidity and the pressure 100 kPa, the moist humidity goes down to 1.075. Okay, so it will give you a sense that at the higher temperature, the air density is lower. Okay, the in this way you can calculate the air density at any humidity, any relative humidity. Okay, and at the dry conditions. Then we need to find that this air density is dependent on which state variables. Okay, so the state variables are the one which define the state of the system when we are observing them. Like if we are observing a system at a particular time, a particular temperature T, okay, and at that time the pore air pressure or the air pressure is UA. So these are the state variables. They define the state of the system. Okay, so we are here to study the sensitivity of the air density on these state variables, basically the temperature and the pressure. Okay, so the formula states that the ratio of change in the air density upon the initial air density is equal to the change in the pore air pressure or the air pressure divided by the initial air pressure minus change in the temperature divided by the temperature. Fine. So the minus sign here denotes that as the temperature will increase, the pore air pressure will decrease. Right? Sorry, the density of the air will be decreasing. Okay, but as the pore air pressure will increase, the density will be increasing. Right? So so this formula will relate with two simple example. The first one says that during a typical yearly cycle, if the atmospheric pressure air pressure remains constant at that is 1 atmosphere, that is 101.3 kPa, and the air temperature varies from 263 to 323 Kelvin. So the air temperature is increased from 263 to 323 Kelvin, and the average temperature is with an average temperature of 300 Kelvin. Okay, so we need to calculate the relative change in air density, right? So for this, we'll use the same formula, that is the change in the air density upon the air density will be equal to, as the first term, the atmospheric pressure is constant, so the first term will be 0, right? Delta UA upon UA will be 0 because there is no change in the atmospheric pressure. But for the second term, that is minus delta T upon T, there will be some changes, right? So we'll put a minus, and the temperature is changing from 263 to 263 to 323. Okay, right? So I think it is written incorrectly. 263 will be this side and 323 will be this side because the temperature T1 is 263 and the T2 is 323, right? So and divided by the initial temperature 263. So and in this way we'll get the ratio as minus 0.228. This means that this change delta PA will be equal to minus 0.228 times delta rho A is equal to minus 0.228 times rho A. That means the change in the air density will be equal to minus times 0.228 times the air density, right? Initial air density. So now, now if we see the similar type of example in the opposite sense, that this time the temperature remains constant at 300 Kelvin. Okay, and the air pressure varies from 80 to 110 kPa. So what will happen? We'll use the same formula, and from the same formula, we'll see that the delta T upon T term will be zero because delta T is zero. There is no change in delta T. It is constant at 300 Kelvin, right? Nobody else is joining. Okay, so it is going to be constant at 300 Kelvin, right? So we'll write the first part of the equation, that is delta rho A upon rho A is equal to the change in the air pressure upon the initial air pressure. Okay, so the change in the air pressure is initially it was 80 and now it is 110. So u2 minus u1 is going to be 110 minus 80. Okay, and it will be divided by the 80. So we'll finally get a change as 0.375. Right. So if we write it here, that is going to be delta rho A is equal to 0.375 times rho A. Fine. So we'll see that the temperature, the factor which is by which the air density is changing because of the temperature is 0.228, and the factor by which the air density is changing in case of pressure change is 0.375. So we can say in case of vapor pressure, the temperature in air pressure change, the air density changes more rapidly. Now we talk about on the second term, that is going to be the viscosity. So the viscosity of a material is a variable which describes the ability of a given fluid to resist flow. Okay. So between two layers, if there is a flow between two layers, then the viscosity defines that how much resistance is there between the two layers of the liquid to resist their flow, right? And for the viscosity also, just a second, viscosity. Okay. So for the viscosity also, we'll do a small example, okay, to see how to solve the problem related to viscosity. Okay, so the question dictates that a liquid and gas conductivity test was conducted using separate constant permeameter for sandy soil with a mean pore size of 10 to the power minus 3. The steady state velocity of air through soil was 10 to the minus 2 meter per second, and the water was 10 to the power minus 4 meter per second. Okay, so we need to determine whether the at room temperature Darcy's law can be used to analyze the test result or not. Okay, so there are other things which are given, that it's the viscosity of the air and water at room temperature to be 1.8 into 10 to the power 5 minus 5 kilogram per centimeter per second meter, and zero point 0.9 into 10 to the power minus 3. Okay, respectively. Then the density of the air at room temperature is about 1.2 kilogram per meter cube, and that of water is about 1000 kilogram per meter cube. Right. So to solve this problem, that how do we check that the Darcy's law is valid or not? So the first condition for checking the validity of the Darcy's law, or the condition for checking the validity of Darcy's law is only valid for laminar flow, right? And the laminar flow is determined if the Reynolds number is below 1. Okay, so for this question, we'll need to check if the Reynolds number for liquid as well as gas is below 1, right? So the formula for the Reynolds number is RE is equal to rho velocity and the size of the pore in which the liquid is flowing, or the pipe, or okay, the diameter, and the viscosity, okay, dynamic viscosity. So in the Reynolds number formula, if first we solve for the flow of the air, okay, so the density of the air, that is rho, is given as at room temperature it is 1.2. So the density is 1.2. Okay, the velocity of the air through soil is given as 10 to the power minus 2 meter per second. So that's going to be 10 to the power minus 2 meter per second. And then the third term, that is the pore size. The pore size is given as It's going to be 10 to the power minus, the mean pore size is given 10 to the power minus 3. Okay, for the sandy soil, 10 to the power minus 3 meter. Okay, so so if we put that here, the pore size diameter of the pore size diameter 10 to the power minus 3 meter, and then we'll need the dynamic viscosity. The dynamic viscosity is given at, consider the viscosity of air and water at room temperature. So for air, it is 1.8 into 10 to the power minus 5, and for water, it is zero point 0.9 into 10 to the power minus 3. Okay, so we'll for air, we'll put 1.8 into 10 to the power minus 5. Right now, if we multiply these terms, okay, then we'll be getting 10 to the power minus 5 is here, 10 to the power minus 5 is here. They'll cancel out 1.2 upon 1.8. So if we solve it, that's going to be 0.67. The 0.67 is less than 1. It means that this is a laminar flow. So this one is for air. Okay. So for air, we have found out that the Reynolds number is less than 1. That means the air is flowing following the laminar flow principle. Okay. So in this case, Darcy's law is valid, right? Darcy's law is valid. Then we move on to the water, flow of the water. So the Reynolds number for the water will be calculated same as that's for that of air. Okay. So for the water, we have the density as given as 1000 kilogram per meter cube. That going to be 10 to the power 3 kilogram per meter cube. The velocity is given as 10 to the power minus 4 meter per second. Okay, so that's going to 10 to the power minus 4 meter per second. Okay, and then we have this pore size that is same as that of air, 10 to the power minus 3 meter per second, 10 to the power minus 3 meter. Okay, then we have the dynamic viscosity of the water, that's going to be zero point 0.9 into 10 to the power minus 3. So now if we calculate uh, on the Reynolds number here, then it is going to be zero point 0.1, right? 10 to the power 10 to the power 3, 10 to the power minus 4. Okay, that's going to be 10 to the power minus 1 divided by zero point 0.9. Okay, that's going to be zero point 0.1, right? Anything which I've left? Okay, I don't think so. So in this case also, the Reynolds number is zero point 0.1, that is less than 1. So this will also be a laminar flow. Okay, so it will also follow the Darcy's law. Right? So both these flows can be explained or analyzed in the test result in the form of the Darcy's law. So the Darcy's law can be used to analyze both of these test results. Right? Okay. Yes, it's there. Okay, now we move on to vapor pressure part. Okay, so the vapor pressure is actually the partial vapor pressure of the liquid vapor. Okay, example is water vapor, and there are two things: so vapor pressure and saturated vapor pressure. Okay, saturated vapor is the one. Vapor pressure is the one which the vapor uh, which the vapor applies on the liquid at the phase of the equilibrium in the phase of equilibrium. Okay, so the saturated vapor pressure for a system of pure water and air, it depends on temperature and total air pressure. But its dependency on total air pressure is very less. Okay, so it basically depends on the temperature. So to determine the change of the saturated air pressure or the dependency of the saturated air pressure, that is UV sat on the temperature, this formula is given by Tetenzen 1930. Okay, so this formula can be used to determine the vapor pressure at the saturated vapor pressure at a particular temperature, right? And there is no term for air pressure because mainly the saturated vapor pressure depends on the temperature. That's why this formula is formulated for the temperature only. Okay, and similar formula. This formula is the similar, but it gives you the saturated vapor pressure in terms of of Hg. Okay, so the third formula is also there. That will also give you the saturated air pressure in the of Hg. right? And for this, you'll need three constant K1, K2, and K3. Those are provided in the table by, I think I forgot to mention the name. Okay. So these are the three formula by which you can calculate the saturated vapor pressure and its dependency on the temperature, right? So I think you might have solved the problem on this in your theory class. Okay. And so there was also one question in assignment number two that assuming the temperature to be constant, the vapor pressure in areas near river bank is less than that of the area near seashore. So the formula for that, the answer for that can be no, because that as we see the vapor pressure is mainly depending on the temperature, and if the temperature is constant, it's going to be basically constant. So now the next term is relative humidity. So relative humidity is defined as the ratio of the absolute humidity in the equilibrium within any solution to absolute humidity in the equilibrium with free water at the same temperature. Okay, you can also write the formula of relative humidity in terms of vapor pressure. That's going to be the vapor pressure at particular humidity and vapor pressure at saturation. After introducing this, we'll move to the assignment number one. Okay, so for the assignment number one, uh, the first question is that shear strength of the soil depends on what? So if we see the shear strength of the soil from the Mohr-Coulomb's formulation, okay, so it is equal to tau is equal to C plus sigma and tan phi dash, tan phi, or in the effective terms, C dash plus sigma n dash tan phi dash, right? So if we can see from the figure which is provided on the right side, then we'll see that what are the forces which are available. The first one are the interparticle forces, okay, and the second ones are the if the pore water is present, then the force due to pore water or the force due to seepage if the drainage is happening. Okay, so in this way, from the formula also we can see the shear strength of the soil. It depends on what? It depends on first the stress, that is the effective vertical stress. Okay, and also on the these C and phi values. Okay, so these shear strength is also affected by the drainage conditions. Okay, and the soil water content. Fine. So for this we can say that the for this, we can say the shear strength of the soil depends on all of the above, right? And coming to the second question, it's basically on the consolidation test again. Okay, so it asks that the consolidation test data are used to determine what? Okay, so for the consolidation test, we usually perform at the end. We want to determine the coefficient of consolidation. Okay. Before that, we calculate other quantities also, such as the coefficient of compressibility, compression index, recompression index, coefficient of volume compressibility, as we discussed earlier. Okay. But the final motive is to determine the coefficient of consolidation that can give you idea about the consolidation that is happening in the soil sample. And with this, I think you can answer the question number two also. And sorry for that. And then we check who else is there. It's a message. 3546. The question number three is that for the derivation of 1D Tarjagi's consolidation equation, what are the one-dimensional Tarjagi consolidation equation? What are the rules which are involved, or what are the conservation what are the terminology which are involved? So for 1D Tarjagi consolidation, it is basically conservation of mass is involved.
Okay, so the mass is conserved while doing consolidation. The while starting the conservation, Tarzagi's consolidation equation. Along with that, we also the conservation of momentum is not involved, and we also take care that while we study the Tarjagi consolidation theory, we assume that the small strains are happening in the soil. Okay, so the small strain assumption is also involved. Apart from that, in the list of Tarjagi's theory assumption, the Darcy's law is assumed to be valid for the soil, right? So in this one, I think three options can be valid for this. Okay, and the fourth question of the assignment talks about the partial vapor pressure during evaporation varies with, right? So the partial vapor pressure is basically if they are several gases, so there is a separate vapor pressure for different gases. So that actually represent that what is the partial vapor pressure of a particular component or particular gas, right? So the first option is the density of the vapor. So the density of the vapor mainly depends on the what are the temperature conditions, etc. Okay. Then the temperature. So there is one example which I have represented in the figure here is that there are two environmental conditions A and B, and the pure water is there. In the first condition, the temperature is like 25 degrees, and the second condition temperature is like 40 degrees. Okay, and the pore air pressure is the air pressure is all atmospheric pressure that is all is same in the both. Okay, and the volume is same in the both. Okay, but you'll see that for the first case, that the temperature is low, less vapors are there in the environment, and for the second case, the more pressure are there in the environment, right? So from here we can see that the vapor pressure mainly depends on the temperature. Okay. And the kinetic energy of the vapor molecules also depend on the temperature. More the temperature, more is the kinetic energy of the vapor molecule. Okay. And the relative humidity is a term which also depends on the temperature. It is basically inversely related. So if the temperature is more, so the particles in the air they have more capacity to absorb the water, like right. So the relative humidity will be less, right? So it's like that. So the relative humidity and temperature are inversely related. So at the end, if you'll see the independent dependability of these variables, then you'll find that the partial vapor pressure is dependent mainly on temperature. And question number four we have covered. Then as we come on to question number five, for the direct shear test, the peak shear stress increases with increase in the normal or confining stress. So before answering this question, we'll just have a look that in the direct shear test, how do we perform? So there's a shear box, okay, where we place two samples and we make one interface in between the samples, right? So and we try to provide the shear force in the sample to calculate what friction is there. So we basically calculate the CM5 values, right? So before that, we also apply a normal load on the sample. Okay, that is shown here. Okay, so we also apply a normal load here. The laser pen. Okay, so for the application of this normal load denotes that uh, uh, when we increase this normal load, these two interfaces are more close, okay, and they have lesser resistance to any shear force that is happening here. So here I have shown one particular data from the normal flow for this shear box test, okay, or the direct shear test. Then you'll see as the normal load is increasing, this graph is going above, or the shear stress of uh, these the same sample is increasing. Okay, so from here we can say that in the direct shear test, the peak shear stress which is there, this point it basically depends on the what normal loads we are applying, right? So this statement can be said to be correct in this in that sense. So the peak shear stress increases as we increase the normal or confinement stress. Right? Question number 5.
So while we were solving the question in the last assignment, okay, we were about to discuss the direct shear test. Okay, so what happens in direct shear test that there is a direct shear box, okay, in which the sample is kept here. So there are two parts of the sample, okay, and the upper part of this apparatus is given a shear force, that is px, and we calculate the friction that is happening or the resistance which the soil is giving after the application of this shear force, right? So a normal load is also applied on this one. Okay, so the slip surface here is assumed to be horizontal. Okay, and now if you'll see here that while we look at the typical result of this direct shear test, we'll see that for the dense case, for the loose case, the horizontal this is the y-axis is the horizontal force, or we can also say the shear force. Okay, so the shear force will increase with the horizontal displacement. It will keep on increasing, and it will reach at saturation, right, or a particular value after which it will not increase. That is called the critical state shear stress, right? And in case of dense sand, this will first keep on increasing at a faster rate. Then it will reach to a peak value that is called peak shear strength. And after that, the sample will lose its strength and it will again reach at the same place that is called the critical state shear strength. Right. So they for the dense case, there are two values which are obtained. The first one is the peak shear strength, and the second one is the critical state shear strength, right? Or the peak shear horizontal force or the critical strength or the horizontal force, right? And if we plot these in taking y-axis as the horizontal force or the shear force and x-axis as vertical force or the normal force, right? So in that case, we'll obtain that if we plot these points, these are for the peak stress. Okay, these peak stress, we'll do multiple direct shear test. Then we'll obtain these one, two, three, and four values of the peak stress. Okay, then if we plot this will be like a curved line. Okay, and if we fit a linear line from this point, okay, then from this line we can obtain the value of this phi p or the the value of the internal angle of friction for the peak stress, right? And if we plot the value of these critical state shear stress or the horizontal force at the critical state, then these points will be plotted. And if we draw a line from these, a best fit line, then we'll obtain the slope of this will be phi critical state. Okay. So this is the critical state angle of internal friction, right? So to understand better the result of the actual test, there is a small problem which we'll be solving here. Okay. So there is a shear box test result of two samples. One is sample soil A and one is soil B. Okay, but with different initial unit weights. Okay, and these are showing in the table. And sample A did not show peak value, but sample B did. So that means sample B is the dense, and sample A is the loose side, right? So for the sample A and sample B, the test results are shown here. The vertical force is this one, the horizontal force is this one. For sample B, the vertical force is this one, then the horizontal force is this one. So what we need to determine the critical state friction angle, the peak friction angle at vertical forces of 200 Newton and 400 Newton for sample B. Okay, because for sample A, it does not reach the peak shear strength, right? And then we'll calculate something called the dilation angle, right? So for the same stresses, 200 Newton and 400 Newton for sample B. Okay. So the step one will be to plot these results on a graph. Okay. So if we plot them on the graph, the horizontal force on y-axis and the vertical force on x-axis, then we'll see that the peak values will be coming here, right? So this value will be corresponding to the horizontal value of around 150 and the vertical value of around 250. This one is for soil B, right? So we are plotting for soil B. So this one is going to be the horizontal stress is around 98 and the vertical stress is around 100, right? Here in the middle. Similarly, if we'll plot other points, then we'll see that this type of curve is obtained. Okay, and if we plot a best fitted curve from this one, then we'll see that for this particular soil B, we have obtained the peak shear strength angle. Okay, that's going to be this. This one is the best fitted line. That's going to be 32 degree. And if we plot the critical state here, critical state values of the which are given here, that's going to be after we reach a peak. Okay, then we'll obtain that we will obtain a critical state friction angle. That's going to be 30 degree, right? So here, if we extract the values from the graph, then we'll obtain that the phi critical state is going to be 30 degree, right? And if we need to determine the internal friction angle at 200 Newton and 400 Newton, then that we can obtain from the value that is going to be this the slope of this line tan inverse the at 200 Newton the value of the horizontal force is 175. So that's going to tan inverse 175 upon 200. So it will give you a value of 41.2 degrees. Okay, and at 400 Newton, it will give you a value of tan inverse 248 and the vertical force is 400, right? So it will give you a value of 31.8 degree. Right? So now we need to determine the dilation angle, that is the angle between the phi peak and phi critical state. Okay. So this angle we can calculate at 200 Newton. The phi peak is 41.2 degrees minus the phi critical state is always constant at 30. Okay. So it's going to be 11.2 degrees. And for 200 Newton, for the same as 400 Newton, so it's going to be 400 Newton. Phi peak is going to be 31.8 and phi critical state is going to be 30. So dilation angle will be 1.8 degrees, right? So here, the thing to note here is that if you'll see, we have conducted several tests, three tests here, four tests here. If you consider the sample B, because it has reached the peak value, then critical state. So we'll see the critical state friction angle is not varying with the normal loading conditions, right? It is going to be constant, that is 30 degrees. If more tests will be performed, then they will always lie in this line or a little bit here and there. Okay. So the critical state friction angle is not dependent on the normal stress, right? But the peak shear strength angle, that is the peak shear strength angle is dependent on the what is the normal stress that is applied, the 200 here, 400 here, right? So this is one of the question in assignment number one, that the critical state parameter phi c the friction angle is dependent on normal stress or not. Okay, so now I think you can answer that one. And the another question was that the angle of repose it can be greater than the angle of interfriction of sands or not. So for that, if you'll see that angle of repose is that if you'll drop the dry loose soil or the dry soil, then this angle which a heap of a dry soil make, that is the angle of repose, right? But in sand dunes, you have seen that this angle can be much greater than the angle of repose. So in unsaturated conditions, okay, these angle of repose can be greater than the angle of friction. Mostly what is assumed that this angle of repose is equal to angle of friction. But in the unsaturated soil conditions, this angle can be much greater than the angle of repose, right? So now, as we move on to the next question of the assignment number one, we'll understand the consolidation test. Okay. In basic soil mechanics, we all read on consolidation test. So I'll just brush up what is consolidation test. So in the consolidation test, we have a soil specimen. Okay. Then we apply some normal loading. Okay. Then with time, the loading, as we keep the loading constant for in intervals, we keep on measuring how much settlement is happening in the soil sample. Okay, this settlement happens and soil is kept at saturation, and this settlement happens as the water leaves the soil matrix, right? So from the consolidation test, if we plot the void ratio versus the effective stress curve, then we'll obtain this curve will look like this. Okay, so this is the compression part. This is the when we release a sample from the normal loading. Okay, then this is again the compression part. So compression, recompression, and compression, and then expansion, then recompression part, right? So for from these results, what we basically obtain, the first thing we obtain is called the coefficient of compressibility. That basically, if we consider a very small portion of this graph, or we take it on log scale, then the slope of this will be the AV value, that is coefficient of compressibility, right? So AV is going to be delta E upon delta sigma dash, and a minus is there to show that as delta E decreases, delta sigma, as delta sigma is increasing, the delta E or the white resistance is decreasing, right? The first thing we obtain is the coefficient of compressibility, right? And from the coefficient of compressibility, we can calculate the coefficient of volume compressibility. That is going to be MV, that is nothing but AV upon 1 plus initial void ratio E naught. So if we elaborate it, then we'll have MV is equal to minus delta E times 1 plus E naught multiply 1 upon delta sigma bar for the average effective stress. Right. So in the just a moment. So now, these are the two quantities which we calculate AV and MV. Okay. So these are called the material constants because the value of these constants depend on, because these are the constants. Okay, and the value of these constant depends on the material which we are using for to conduct the consolidation test, right? So for the to understand the behavior of the consolidation, the Tarjagi have given this equation. Okay, and from this equation we'll obtain that there is one more constant which comes into picture, that is called CV, and the value of CV from the derivation, if you remember, that will be equal to K, that's permeability upon the unit weight of water multiplied by the coefficient of volume compressibility. So this CV is called the coefficient of consolidation. Okay, I think I've not shared my slide. Just give me a second. Stop presenting. Present 2 PowerPoint. Okay, I hope my slide is visible. Okay, fine. If it's not visible, please do let me know. Okay. So K is the permeability of the soil in the direction of the flow, and if we from this consolidation test, we can also obtain the formulation for the settlement. Okay, and the formulation for the settlement is going to be CCH naught upon 1 plus E naught log at the base 10 sigma the sigma naught dash initial stress and the change in the initial effective stress and in the effective stress and the initial effective stress at the denominator. Fine. So the consolidation equation, that is the 1D consolidation equation given by Tarzagi, that is the governing equation to solve the consolidation problem, and it can be solved using Fourier series and with the help of certain boundary conditions. Okay, so the one of the boundary condition can be, if you'll see in this soil specimen, as we allow the drainage from these porous stones, the pore pressure at the boundaries will be zero. U at the boundaries will be zero, right? So using certain boundary condition, we can solve this equation. And while we solve this equation, we come up to a term that is called the time factor, TV. Okay, so the formulation for the TV is that CV into small t, that is time, upon H square, right? H is the length of the drainage path, right? So, okay. So, if you see here, this TV is the time factor, and uh, to obtain the value of the TV, two methods are used. The first one is the logarithmic of time method, and the square root of time fitting method. Okay, so in the logarithmic of time method, we plot the deformation versus time on the log scale. Okay, and then we obtain the time corresponding to the 50% settlement using certain rules, that is small t50, right? And in the square root of time fitting method, okay, we plot the similar deformation versus, this time we plot square root of the time. Hmm. And here in this method, we obtain under root of T90, that is the square root of 90 time at the 90% consolidation, right? So if we know the time of the 50% or time of the 90% consolidation, okay, and we need to determine the CV, and the length of the drainage path we already know is h by 2. The height of the specimen is h, so length of the drainage path is half of it, okay, and the value of the TV is constant for for 90% and 50%, we usually remember the value of the TV, which is constant at 0.848 at 90% and 0.197 at 50%. Okay, so in this way, the only unknown is the CV. So we can calculate the CV from here. Okay, so this way, these two methods are used. Okay, and the time factor which is there, it basically depends on UZ, that is called the degree of consolidation or the consolidation ratio. It represents that how much consolidation has already happened in the sample. Fine. So if we'll if you'll see here the time factor, these two formulas are provided. The TV is equal to pi by 4 U by, or this is the degree of consolidation in percentage upon 100 to the whole square if degree of consolidation is less than 60%, and if it is more than 60%, then we can use this formula. Fine. So the thing here to note is that the time factor depends on the degree of consolidation. Okay. So one of the question is consolidation behavior is dependent on coefficient of permeability. So if we look at this formulation here, okay, this is the coefficient of consolidation which determines the consolidation behavior of the material. CV is a material constant and it determines the consolidation behavior of the material. It depends on the coefficient of permeability, K, right? So in that case, you can, I think, answer this one, that consolidation behavior is dependent on the coefficient of permeability or not. Okay. Now we come up with the question, the compressibility modulus of the soil specimen is constant during consolidation. So the compressibility modulus is actually the inverse of bulk modulus. Okay, and what is bulk modulus? Bulk modulus is the increase in pressure divided by the volumetric strain which is happening in the material or the body which we are taking into consideration. So that's going to delta P upon, that is the volume change is negative, so minus delta V upon V. Okay. In consolidation test, this volume change is happening because of the height, so we can write delta H amount H. But if you'll see the increase in pressure, so in the consolidation test, we and the loading which we apply, the normal loading, that is kept constant for a certain interval. So there is no increase in pressure, right? the pressure is kept constant for a certain amount of time. Okay, so this question I think then you can answer, and this question can be answered by remembering the assumption which are involved while deriving the Jaggi one-dimensional consolidation equation. Okay, so the assumption is that certain soil properties such as permeability and modulus of volume change are assumed to be constant during the phase of consolidation. Then we have this question that coefficient of consolidation CV represent the effect of permeability and the compressibility of the soil on rate of volume change. Okay, so the coefficient of permeability CV, if you see that it is asking if it represents the effect of permeability, okay, and the compressibility of the soil on the rate of volume change. So the rate of fall, if we take out the terms from the derivation of one-dimensional consolidation equation, then we'll obtain that the K upon gamma W is multiplied by delta U upon second derivative of the pore water pressure is equal to the volume change in the sample that is happening. Okay, so the permeable CV represents the CV is mainly dependent on the coefficient of permeability as well as the compressibility. And coefficient of permeability affects the volume change, or uh, it represents the volume change behavior of the material. Okay, as well as the compressibility modulus which is there, it also represents the volume change behavior of the material. Right. So these two affect the volume rate of volume change of the material or the soil. Okay. Right. The next question is that material constants may also depend on state variables. Okay. So basically, the material constant, like in consolidation equation, are AV, MV, and CV, right? Which depend on the material and they are constant. And the state variable which are there are pore water pressure. Okay. So void ratio. Okay, so these are state variable which defines the state of the material. Okay, so if you'll see here, the material constants, they are basically the property of the material. They depend on the material which we are using. Okay, so they do not basically depend on the state variables, right? Now we have this equation. This question, the time factor TeV, it depends on the average degree of consolidation or not. So this I think I've already covered here. Okay. The 14th question which was there is that Laplace equation, it represents the transient state seepage of water through saturated porous media. Okay. So if you'll see here, the Laplace equation, which is there in the more generalized form, if you'll see that is equal to kx delta h upon del x2 plus kz delta z upon del x z2 is equal to 1 upon 1 plus e ds upon dt plus s d upon dt. So this equation can have possible four situations in this wide ratio and this as both are constant, right? And if e varies, s remains constant, and s varies and e remains constant, and both e and s are varying, right? So in this case, the Laplace equation which is there, okay, that is basically the kx delta h mod del x2 plus kz delta h mod del z2 is equal to 0 in such form. That is called the Laplace equation. So in this equation, if you will see that if you consider E and S both as constant, that's going to give you the Laplace equation, right? Because the right hand term will be okay, right hand term will be equal to 0, right? So the Laplace equation, what is the transient state seepage? That is representing the time dependent change in the seepage, right? So if the right hand term will be 0, there in the Laplace equation you will not find any term dealing with the time dependent phenomena. So the Laplace equation actually does not represent the transient state seepage, right? Then there's this 15 last number question that's going to be the density of the absorbed water in clays at residual water content at residual water content is very high as compared to the free water. Okay, so there's this phenomena of the diffuse double layer in clays. Okay, so based on this phenomena, if this is the clay particle surface, then the clay particle surface basically have negatively charged particle on its surface. If these and because of this it attracts the positive charged particles and the water that is bipolar that the clay particle will attract the water molecule on its surface, right? So the cation capacity at the surface will be very high, right, and it will keep on decreasing as we go far away from the surface. Okay, and this force is basically electrostatic force between negative and positive charged particles. That's why in this region the water molecule which are there in the absorbed state, those will be very tightly bounded. Therefore, because they are very tightly bounded, the density of the water near the clay surface in the adsorbed water region will be very high. But if you'll see the water which is away from here or here, its density will not be very high because the electrostatic force is very less there. Okay, so in this way you can also answer this one. And as it is 7-6, and nobody else has joined. Let me quickly see who have joined, and I'll note the attendance. Thank you, fine. Okay, so I'll just drop my email ID in the chat box. So if you people have any query, you can directly mail to me. Okay, then I can address that in the next class. And some of you, if you are asking question in that ask question box in the NPTEL lecture, then those actually do not come to me. I do not have access to those questions. Those are handled by the permanent TA which are there with the course instructor. Okay. So my email ID is 21dr0162 at the rate cv.itsm.ac.in. Okay. So I hope you people are receiving the PPT which I'm uploading. And if you people have anything to ask in this regard, please do that. I'll be happy to answer. Okay, then I'll close the meeting here and please do drop me a mail if you need any help or you can ask question in the session also. Okay. Thank you for joining. Thank you, bro. So I'll just close the meeting. Okay.